Okay, so everybody, welcome to the fourth lecture of this series of aspects of higher energy physics. Today we're going to speak about data analysis. So everything that we have been doing until now is about to culminate with this. This is supposedly the last lecture of the series. However, I have been preparing a special lecture for tomorrow, so there is a lecture tomorrow as well, about the reinterpretation of the data. So tomorrow's lecture may be a little bit different, maybe a bit shorter, but I invite all of you to also come and attend. So everything has been culminating to this, okay? We have studied theory, we have studied how to build a detector, eventually to actually build a detector. And we have taken data and reconstructed the data. And now we want to go and analyze this data and see what it can tell us about the physics of subatomic particles. So this is, in a sense, the reason why we're doing all of this. So let me start. Let's go to the introduction to the data analysis. So first, let's make this artificial broad division, okay? We can divide the, let's say, data analysis in two main camps: measurements and searches. So what's the difference? In measurement, one's trying to measure some known quantity, and usually something that's known from the standard model. And this can be something very simple, like for instance, the Higgs boson mass, or in general, the mass of any particle, or the spin of any particle. But it can also be something much more convoluted. What can be convoluted? For instance, you can search for the fully inclusive top quark pair production at the LHC at 14 TeV. So this is a cross-section measurement. So you're counting how many events of this kind you have. And of course, of this kind is, quote unquote, is making the most work in this sentence. What does of this kind mean? And then you can calculate these cross sections in a differential way. I mean, as a function of any quantity one. So for instance, in this case of the top quark pair production, you could calculate it as the invariant mass of the top quark pair, or as the PT of the top quark pair, or as the PT of any of the tops, so on and so forth. Then there are searches. And searches are kinds of analysis in which one tries to uncover the evidence of the discrepancies in between the standard model predictions and observed data. So what does this mean? This means that you're searching for new physics, physics beyond the standard model. And can be anything: searches for new resonance, for new particles, searches for supersymmetry, searches for dark matter, searches for anything that's not in the standard model, which obviously is something which is much larger than the standard model itself. But notice that this distinction is a bit artificial, okay? Because for instance, consider the Higgs to muon process. Higgs to muon is something that is predicted by the standard model. The problem is that it's a very rare process. It's something like 12.08 femtobarn. We haven't observed this yet. The standard model predicts it. but we have not observed it yet. Why is it so small? Because the Higgs boson couples to the mass of the particles, and the neon is not so much massive. So this has not been observed, so we call it a surge. If we were casting this analysis in a measurement, or in a way to measure the sigma proton-proton to Higgs to muon-muon, we would come up to the conclusion that it's compatible with zero. Oh, Thiago, but that means it doesn't exist. No, it means that we put an upper limit on it. Oh, it has to be larger, it has to be smaller than such a number. And the things that the theoretical prediction, this 12 of femtobarn, are smaller than this upper limit on the cross section. So we call it a surge. On the other hand, for instance, when you search for a new resonance, for instance, protons going to Z prime, going to electrons, we will usually make multiple assumptions on the value of its mass, of its spin. We are going to search for a Z prime with such mass, such spin, such couplings. And then we try to measure its production cross section. And if it doesn't exist, we will come up with a value that's compatible with zero. My bottom line is that the distinction is artificial, but it's still useful to keep in mind. Now you may ask me, okay, Thiago, but what do we actually measure in the end? And this is actually one of the simple answers. We count the number of events in a given configuration. So let's say that you want to measure the cross section of TT bar production, top quark pair production. It's simple, right? You have to calculate how many pairs of top quarks you observe. But remember, you don't see top quarks. You see the reconstruction of their decay products. So it's hard to actually do this counting. But in principle, we just need to count events. So here I'm going to define the observed number of events for a given physics process, and observed, which is sigma times L times A times epsilon. And what are each of these factors? Sigma is the production cross section. So this is what nature gives us. So this is the probability. So this is purely theoretically driven. We know how to calculate it because we know how to do Feynman diagrams. We know how to do the matrix elements, right? It's something that you calculate something like this. So this we know. But what about the other numbers? L is what's called the accelerator luminosity. And this is a measure of how many particles you are able to fit through a given space in a given time. I am not sure if we actually discussed it on the second lecture, but this is essentially a measurement, not a measurement, sorry, a measure of how many collisions per second your accelerator can give you. Then the collision happens. A is the acceptance. How many of these particles actually go into your detector? Because remember, even though you have your detector as a layer of detectors around the collision point, some of them don't go there. Some of them go into the cracks that I discussed, for instance, in the in the third lecture. Some of them go down the beam pipe, where the particles are coming from. Some of them go in this direction, so they're actually not detected also. So in principle, this is also theoretically driven, right? Because it's a purely theory quantity. Oh, how many particles go in this direction? It's something that nature gives us. But we usually factor out the production cross-section from the geometrical acceptance. And last but not least, there is the selection efficiency, which is essentially, given that this particle actually went into my detector, what is the probability of me actually reconstructing it as a particle that I can measure? And this, in this selection efficiency, we subdivide into two further parts, epsilon 0 and epsilon A. Epsilon 0 is the efficiency of reconstructing a given set of objects in the detector. So given that you get an electron, for instance, in your electromagnetic calorimeter and leaving a track in your tracker, what is the reconstruction efficiency? What's the efficiency of actually finding that your algorithm actually finds, get that electron and gives you its quantities? And epsilon A is the efficiency of any further requirements that you do in the analysis. For instance, let's say that you are interested in events where the electrons, where two electrons are, let's say, very well separated. Why is that? Because you are interested in this kind of events, or events that have one electron and one muon, and then they have different charges and they are separated by an angle, or their invariant mass is close to some number. For instance, if you want the invariant mass of the system to be close to the mass of the Z because you're interested in Z boson physics. So you decide this. You as a physicist decide this. And here is where you can give rise to your creativity. Oh, I am interested in Z bosons. What kind of analysis should I do? I'm interested in top quarks. What kind of analysis should I do? I'm interested in dark matter. What kind of analysis should I do? So this is the fun of the thing. Now, when I go back and say, we count the number of events in a given configuration, this given configuration is essentially determined by the acceptance times efficiency product. Why is that? Because all of these two things, the production cross-section and the luminosity, are given by external factors. This comes from nature, this comes from the accelerator people. These come essentially from the construction and the reconstruction process and the reconstruction algorithm of the detector. So this is in our hands. And this is also in our hands. So when we choose this given configuration that we're interested in, and then the total number of events that we observe in that configuration is given by this sum here. So this sum is all of the physics processes collision physics processes that produce events in that configuration. And these are spurious combinations from any kinds of non-collision effects. Thiago, I don't understand. Doesn't everything come from physics? Yes, but I'm separating into stuff that comes from, that is related to the collision and stuff that is unrelated to the collision. So for instance, if I'm interested in electrons, Z going to electrons, sure, Z gives me 2 electrons, but something like WW can also give me 2 electrons plus other stuff. In this particular case, plus neutrinos. So it's not easy to disentangle these two things. While n fakes here means anything that could be that looks like my signal, but comes from non-collision effects. So what kind of non-collision effects? Can be anything, right? Can be noise in the detector, errors in the reconstruction algorithms, a lot different kind of stuff. I'm going to give you some examples here in slide number 5. So for instance, the detector is on Earth. Earth is showered all the time by cosmic rays. So sometimes cosmic rays go through the detector and they can give rise to fake muons. Or you can have a beam halo. So the beam is coming and is going to collide inside of the detector. But, so here's the detector, the beam is coming here. But sometimes something strange happens before and some other particles are accompanying the beam here. And these don't really collide in the center of the detector, but they may give a signal here around here somewhere. Then there are hardware failures and software failures, as I said. Sometimes you may have hot cells, so a crystal that a crystal in the calorimeter, which for some reason has a dark current in its photomultiplier, so it's actually always firing, always giving the maximum signal. Or on the other hand, the electronic circuit died, or every once in a while the circuit is unstable, so it gives you a high voltage spike. Or your reconstruction software may fail. And what you thought it was, let's say, a large number of tracks or a large configuration of hits in the calorimeter may end up being a corner case of your software, a bug essentially. And these are funnier, right? You may be asking yourself, what do you mean by the phase of the moon? Are we doing astrology now? No. But remember, the phase of the moon leads to tide effects. And tide effects, well, you can see them in the sea and in the rivers, of course, but they affect everything. And if your experiment is so precise, it may happen that just a little bit of misalignment, say something like 10 to 20 microns, may be enough to change your results. Or the seasonal variation of rainfall. It rains more on summer than on winter. So the earth, the ground, it may swell a little bit because it's more humid. So that again misaligns. Or sometimes, remember, CERN is in Geneva, right? Which is in the border of the French and countryside and Switzerland. And there is a train that goes from Geneva to Paris. It's TGV. And that train goes every once in a while. There is a schedule. And when that train passes by, it electrifies a little bit the tracks, and this subtly changes the ground point of the Earth. And you can see that there are links here, okay? So I will invite you then to look at the links and see that these are all actual true effects that were observed at the lepton, at the Large Electron Positron Collider. So all of this is background to your search. Sure, when you know that there is background to the search. If you have worked in your modern physics lab, if you have had that class, you know that there is a lot of stuff that you cannot control. And when you're doing low precision measurements, it's fine. But when you're doing high precision, you have to really think of everything. But this is just a digression. Okay, let's go back to collision processes. So if we forget the fakes for a second, notice that the sum of number of events observed, it has to go over all the physics processes. And you know that, right? You know that when you are calculating a final state, you have to consider all the possible intermediate states in quantum mechanics. But you cannot ask a final state, hey, but from which process did you come? We cannot really separate the process in which we're interested. So we categorically make the separation in our analysis, but in an event-by-event basis, you cannot know if an event came from one process or from the other. So let's formally do the separation. We are going to call the process in which we are interested the signal, and everything else the background. So if you're interested in Z2E, WW2EE plus 2 neutrinos is going to be your background. But if you're interested in WW, then Z is your background. It depends on what you want to measure. And then we're going to split the backgrounds into two kinds. Irreducible backgrounds, which have the exact same final state. So for instance, non-resonant diphoton production is an irreducible background to Higgs boson production and decay on that channel. So proton going to gamma is the exact same final state in general as the process that goes through the Higgs boson production. So there's nothing to do here. You just have to know this process very well and consider it as a background to this process. Reducible backgrounds are those where you have a chance to find. The final state differs a bit from our signal, but due to some reason, it ends up being selected in our analysis. It appears in the events that we're interested in. So for instance, if you're interested in some kind of search that has ZZ going to 2 leptons and 2 quarks, Z2 leptons plus anything could be a background, because anything could be a hadronic jet, which could be mistaken for the Z2QQ leg. Or on the other hand, if you're looking for Z2LL and want to fight against on the WLL plus neutrinos, you can ask for there being no missing ET, which has a chance of discarding events that have neutrinos. So the key thing is that you want to separate by it being the exact same final state or not. So these are the diagrams that that explain in pictures what I meant. I'm interested in Higgs production going to gamma gamma, but these other processes also exist. And you just see the two photons in the end. You cannot really know what happened in the middle. So you have to model these two very well to consider them as a background to this. Here, on the other hand, in the bottom, this gluon can give a jet, and maybe these two quarks give one or two jets, but it may give one jet. And then this thing looks a lot like this thing, two leptons and one jet. But then you have to fight against this by looking into characteristics of this jet that comes from one gluon from this jet that comes from two quarks. Okay, how do I do that in practice, Thiago? You have to search for observables that are distributed differently for signal and background. For instance, for Z to LL is easy, right? You know that if you want to search for the Z decaying to leptons, the Z has 90 GeV. So usually this much mass will be shared in the form of energy for the leptons. So they will be high PT leptons. They will have the same flavor. So either 2 electrons or 2 muons or 2 taus. The Z is neutral. So they have to be opposite charge. And you know that the Z mass is something like 91 GeV. So you can search for events that the invariant mass of the two leptons are around this range. And this is enough. Z is extremely pure. Look here. This is the data. And this is Z to 2 electrons Monte Carlo simulation. It's extremely pure. If you just do this, you will have a sample of events which are almost completely dominated by Z. So this is easy. Some stuff is harder. For instance, if you want to search for supersymmetry, assuming that you're searching for one given final state, for instance, supersymmetry giving you leptons and jets, you can invent these complicated variables that have that take the missing transverse momentum and the momenta of two jets, and make these complicated calculations here. So the MR and the transverse MR, and calculate this R square here. And then you try to compare with data and simulation in many different regions. So all of these parts here are different histograms. We're just putting them all together for visualization. And you can see here that unlike this case, where there is only one process, V2E, here there are at least 3 that we count. 4, right? Light blue, dark blue, red, and green, which is different stuff, doesn't matter. But you can see that it's a much more complicated analysis. But Thiago, I'm sorry, why did you invent this stuff? This is the creativity. You have to think about the analysis, think about the topology that you're searching for, and try to design this kind of variable and see if it works. Of course, nowadays we live in the future, right? This is 2021, so maybe we don't need to do that. Maybe we can just train a computer to do it for us. And yes, we do that too. So you people who are aware of artificial intelligence and machine learning know that in principle, you can simply give the problem to a computer and tell it to find me some variable implemented in a neural network that separates signal for background. Here is a sample signal. Here is a sample of background. Go home. And this is machine learning. And it works, okay? Machine learning is extremely extensively applied in higher energy physics these days. And there are the two things that I just said. You can have classification problems. For instance, say that the event is signal or background. Although we do something that the people in machine learning analysis, in real computer science, don't usually do, that instead of just asking the computer to do the classification, we go one step back, we unpack the classification, look at the output of the machine learning, and then try to work with this histogram here. And you see here, okay, it's a bit hard to see, but you can see that there is the signal, look here, light blue signal. It concentrates on these values of the variable that are more or less above 0.40 something. So, but Thiago, what is this variable? Nobody knows, right? It's the output of an artificial neural network that was trained to know how to separate all of the backgrounds, so everything else, from the signal. And you see here that indeed, this region here is enriched on background, and most of the signal is on this side. But there is, of course, also a lot of background on this side too. On the other hand, you can also use machine learning to do regression problems. And the difference is that in classification problems, where the output variable takes discrete values, so class labels, signal or background, type 1 or type 2. In regression problems, the output variable will take continuous values, so a real number. And this is useful, for instance, in reconstruction, because you can calculate, you can correct, let's say, the energy of a jet from a dihadron based on its kinematics, its flavor content. Let's look at this example here. If you want to calculate Higgs to be the bar, and you want two jets that come from dihadrons, you have, before using the machine learning technique to correct the jets, you have that the peak is not really 125, right? It ended up being horrible, but I can do this, nice. See, it's not quite on 125, it's more or less 110. But if you use the correction after training the machine learning to learn and apply this correction, you have something that is closer to the real value, 120 something. So machine learning is one of the newest and, dare I say, best tools in the toolkit of the modern high energy physicists. Fine. But of course, there is one problem. You cannot really interpret the machine learning output. Understanding what the machine is learning is a research problem in computer science. It's not something that even us high-end physicists can tackle. So sometimes we have to go back to basics. which is the so-called cut-based analysis. And what are cuts? Cuts are thresholds that you apply to your selection. So for instance, you say, I want 2 leptons with PT above some threshold, let's say 20 GeV. So this is a cut. The value of the cut is you want the PT to be above 20 GeV. I want the pseudo rapidity to be less than 2 or something like that. So and I want the angle to be above, I don't know, pi/3 or something like that. So you design this to try to select signal and reject background. But here's the key. You want to do this in an unbiased way. And the idea is that we usually do this in blind studies. What are blind studies? You design all of your cuts and all of your analysis in simulated data. And then you tune, you optimize, and only then you run the analysis on real data and unblind. And now in these COVID times, you probably have heard this already, the double blind study, right? So in the COVID case, you give the vaccine to a group and you give placebo to another group. Either of the groups don't know if they took vaccine or placebo. And the experimenters themselves, so the scientists doing the study, also don't know which group is each. And in this way, we avoid both the observer bias and the confirmation bias. In our case, we don't have to be double blind in that sense. We only have to blind ourselves. We design the analysis, do everything, and only then look at the data. Obviously, the protons are not conscious, so they don't think. We don't care what they think because they don't think. In the case of an analysis where both of a study in another field, where both the subject and the experimenter are conscious, then of course you have to blind both of them. So the idea is that you choose cuts that optimize the final overall accuracy of the result. And here I'm using accuracy in a loose term. You have to choose a figure of merit that you want to optimize. And this can be different figures of merit, right? Because you may want to have, the maximum amount of signal, or the best ratio of signal to background, or the least amount of background. All of these are different things, and you cannot optimize usually for all of them at the same time. Of course, there is a trade-off to be done here. The trade-off is that if you cut too much, you may end up with very little data, and then you have low statistical power. And in general, but it's a more general thing that you have to trade off in between statistical and systematic uncertainties. And you'll see more of this later. So the key thing is that you have to always study the marginal effect of your cuts by tables and plots. You always have to see, okay, what is this cut actually doing? Cuts that have no marginal effect, so if together with all the others, they don't remove any event, so they do nothing because all of the selections that they were to make are already done better by other selections, they're useless, so you should remove them. You can see here on the right the effect. Remember, efficiency times acceptance. You can see here the effect of 6 different kinds of cuts on a search for resonant ZZ production, so something like proton-proton, going to a new resonance, going to ZZ, as a function of the mass of the resonance. And you see that the cuts have varying efficiency times acceptance, depending on this variable. So that's why you have different sets. If you're searching for low mass resonance, this red set of cuts, which is called resolved untagged, has the highest efficiency, something like 30%. But then it decays quickly. While this one, merged untagged in green, raises up and then more or less stabilizes at something like 40%. All of these others, like merged be tagged, resolved be tagged, are additional sets of cuts that represent corner cases. And then you want to analyze all of these data, all of the data sets separated by each of these cuts separately and do a statistical combination in the end. Oh, sorry. However, there is a problem. Even after you do all of this, you write cuts, you optimize for the best signal or the best signal over background ratio or the least background. In general, you cannot get rid of all the background. There will always be some background that remains. And then you have to estimate how much background remains. There are some options. Either you just simulate everything and trust the simulation, which we usually don't do, or you correct the simulation with some kind of correction factor that you do by defining control regions. For instance, so let's define some particular set of cuts that is called a sideband, which looks like the signal, but has some subtle difference. And in that subtle difference, the signal dies. And then I have a region that is completely dominated by the background, but is a special kind of background that looks like my signal. And then you compare these control regions in simulation data and use this comparison to correct the simulation. Or you can model your background, what's called in situ, which is more or less the same thing as above, but you do it serially, in such a way that your control regions act simultaneously as measurement regions for some other kind of research. For instance, if you look at the dye-jet spectrum, so this is the mass of the two jets in the LHC. It is something like this. And if you're searching for new physics, you are searching for deviations of this soft curve here, of this smooth curve, so bumps. And the idea is that region by region, you can do something that looks like, oh, let's say that on the left I have this, on the right I have this, then I would expect something like this in the middle. Do I see it? No, so exclude. Then you move to the next region. Now, this is the control region, this is the control region, and you use these two to estimate what I would expect from the middle and see if I see a bump. I think I have this example in the next slide. Oh, sorry. Sorry, misclick. Ah, yes, here we go. So this is exactly what we do. You do this, you have this data, you fit them with this function, and the fact that it's a global fit means that if there were to be a bump here, all of the rest of the regions would try to constrain what is expected here in the middle, and then you don't see any difference from the expectation, and then it's a, and then you agree that this bump's not really here. Here it's a bit lower, but it's just for observation, for graphical purpose. The idea is that this bump sits on top of the distribution. And since it's a global fit, a fit to all of the region, this process where every set of other regions constrain a given region. And here on the right, it's this data corrected simulation that I just told you. So you look, for instance, at the PT of a process Z2E, which is mostly dominated by this white histogram here, which is Z2E. And you try to derive some correction factors in between the data and the simulation. These correction factors are not small, sorry, are not large. You see here, the data is the data, the red histogram, see that there is a red dashed histogram here. That is already in very good agreement that in between the histogram and the points. But then you do a fit, and the fit is a global fit, so this is just one of the regions that enter. And then the histogram goes to the blue. And then you use this correction factor to correct the Z to neutrinos plus jets. So the green histogram that appears on your signal region. So here on the right, you have the signal region, and you have all of these backgrounds: V in green, W in yellow, WWZZ and WZ in blue, top quark production, and so on and so forth. So you use many different regions to constrain all the different processes that appear in the selection you're interested in. So the bottom line is you have to understand your background. First, you have to devise cuts that separate signal from background. And then you have to find a way to estimate the background after you have applied all the cuts. But Thiago, my analysis is so good that I managed to kill all the background. It's zero. Doesn't matter. You have to find a way to put an uncertainty on that zero. And then after all of this is done, it's just a statistical problem. I expected 10 events, plus or minus 0.2. I observed 13. Probability to the rescue. I'm going to give you a quick rehash of probability here, okay? I'm pretty sure that all of you people know all of this, but let's go through it. Mathematical probability. This is the kind of things that you learn in the true probability course in the mathematical in your Institute of Mathematics in your university. It has to be the probability of occurrence of some event xi is pxi, and it has to follow the so-called Kolmogorov axioms. Has to be positive, has to be conjoined like this, and has to sum to 1. No probability, the sum of our probabilities has to be 100%. This helps us not much. If you define the frequentist probability, then it's something that we as physicists can work with. If you observe large n events and small n of them are of type large n, then the probability of an event being of type x, sorry, there are typos here, okay? Here it's supposed to be type x. I'm going to fix this later. Is this empirical limit of the frequency ratio. So if you observe 3 out of 10 events, the probability is 30%. But then maybe if you were to observe 100 events, it would be 31. So the probability is 31%. And in this limit, it would converge to the true probability. The problem is that we cannot actually take the limit because we cannot actually make infinite measurements. So we can approximate this probability by making n large, big N large. One caveat is that the experiments have to be repeatable. And repeatable should mean that all the relevant conditions are the same. So if you're, let's say, flipping coins, you should flip the same coin, or at least coins that are identical for all purposes. But what does identical for all purposes mean? This is part of the experimental setup that you have to take care of. Then, of course, there is Bayesian probability, okay? And Bayesian probability is the degree of belief in X. And then there is a lot of discussion in between Bayesianism and frequentist probability. The key thing is that the Bayesian probability is a property of both the observer and the observed system. So it's subjective. And why is this? If it's subjective, it means that it will change if the observer, if you obtain more knowledge. But Thiago, how can this be? The probability is something only that is only a property of the system. No, probability is something that follows the Kolmogorov axioms. These are approximations or operational definitions of probability. So if you follow this definition of Bayesian probability, you can show that this follows the Kolmogorov axiom, so it's done. But has this property that is subjective. Also, think about it for a second. What's the probability of raining tomorrow? In frequentist probability, there is no answer, right? There is only one tomorrow. There is only one August 6, 2021. It rains or not. So what does probability mean? Frequentist probability would mean there are no repeatable tomorrows. But we may still want to try to answer if it's going to rain tomorrow. Or what's the probability of the universe being flat? or what's the probability of the Higgs vacuum being stable? So bottom line, we are not going to solve this here. I just want to draw your attention to this, okay? And by the way, there is some work on studying objective Bayesian statistics, but this is a very active field of research in mathematics. So work to be done still. By the way, this is what I mean by, in slide 15, this is what I mean by what does it mean that the Higgs vacuum is stable or not? Turns out that if the Higgs, if you calculate the probability of the vacuum, sorry, if you calculate the properties of the electroweak vacuum, remember from the first lecture, remember the Mexican hat thing? It may turn out that with some quantum corrections, the vacuum may destabilize. The potential goes from something like this to something like this, which means that there is no true vacuum, there is no lower energy state. And these quantum corrections depend on the Higgs mass, to first approximation, and the top quark mass. And by quantum corrections, I mean also higher order corrections in the perturbative expansion. But bottom line is that depending on the value of the Higgs mass and the top mass, the vacuum may be unstable, it may be stable, or it may be metastable. What does metastable mean? Metastable means that, yes, it's unstable, but the time of instability, so the time that the vacuum destabilizes, is larger than the age of the universe. So we're fine. And then we are here. This is the measured value, and these are the 1, 2, and 3 sigma contours. So it's surprising that we're here, right? We would prefer to be here. If we were here on the unstable part, we wouldn't be here talking about there would be no universe. Okay. Enough of this instability of the vacuum. Let's go back to simple probability, stuff that we can actually calculate. Let me quickly tell you about something called the Bayes theorem. So for discrete events, you can, I'm not going to demonstrate, but you can prove that the probability of A given B is the probability of B given A times the probability of A divided by the probability of B. If you do a Bayesian probability framework, you can call this B and A, you can call them something like parameters of the model and observed data. So let's read this again. The probability of the parameters of the model being this, given that I observed this data, is the probability of me observing the data, given that the parameters of the model are these, times the probability of the parameters of the model being these, divided by the probability of me actually having observed this data. But Thiago, how can it be the probability of the parameters of the model? The parameters of the model are what they are. Yes, this is correct. But again, we want to talk about these things. When you say that the mass of the electron is such and such with such and such error, when you say error there, you really want to say that you really mean that you have a point estimate and an interval of confidence. Confidence interval, sorry. You really mean that I believe that there is a 68%, right? 1 sigma. 68% chance of the true mass of the electron lying in this range. You are familiar with this, but you are not used usually to think about it in terms of probability of the parameters of the model. So now that and of course, if you do instead of discrete events, continuous random variables, it comes like this. So now we can say, oh, the probability of the parameter given the data is a probability density function. Fine. But this thing here, the probability of the data being what I observed, giving a parameter, is not a probability density function. It's what's called the likelihood function. And you can see this because you see that this thing does not integrate to 1. Remember, probabilities have to add up to 100%. And last but not least, this P of theta is the prior probability density. So the probability that even before starting looking at the data, what's the probability for this, for the parameters to actually being this? And if you subscribe to Bayesian statistics, this is exactly the subjective part. And this is where lies the major problem. Notice that, of course, this is Bayes' theorem, but the theorem itself is true. It's just a mathematical theorem. It's true in frequentist statistics, it's true in Bayesian statistics. But it's the interpretation of this prior probability density that is problematic. In Bayesian statistics, this is your prior degree of belief. What is it in frequentist statistics? Yeah. Complicated. This is an example that comes straight from Wikipedia. Okay, so let's work with it. That you'll see some. That will get a bit of what I'm trying to say here. Imagine that you are an entomologist and you're studying beetles. Then there are 2 subspecies of beetles. One that is common and one that is rare. And then you go and spot something that might be a rare subspecies of beetle. Why? Because it has some specific pattern on its back. Maybe the common beetle has spots or something like that, but the rare beetle is the same species, but it has a cross, blah, something like that. Now, this is not true for all beetles because in the rare subspecies, 98% have the pattern, but not all. In the common subspecies, by sheer luck, 5% the dots sort of align and it looks like, and it ends up looking like a cross. So probability of X given R is 98%. Probability of having the pattern given that you are in the rare subspecies is 98%. Probability of having the pattern given that is the common subspecies is 5%. Now, the rare species is only 0.1%. It's really, really rare. But you found the beetle. How likely is the fact that is the beetle having the pattern to be rare? Or what is the probability of it being rare given that it has the pattern? You should be pretty sure, right? I mean, come on. Only 5% of the common beetles have the pattern. Almost all of the rare beetles have the pattern. And this beetle that I have here on my hand, it shows the pattern. What are the chances? Well, the answer to what are the chances is exactly what Bayes' theorem gives to us. Probability of R given X is probability of X given R times probability of R divided by, and here I made a mistake again. Let me just go back here. And yes, it's supposed to be the probability of X. Sorry, X. And we have all the numbers, so just run them. And you get that the probability of the beetle that you have in your hand actually being of the rare subspecies is less than 2%. Sorry, you didn't find the rare beetle. In statistics circles, this is known to be as the Bayes rate fallacy. And the idea is that there are so many more rare, so many more common beetles that even though the pattern is much more common, overwhelmingly more common on the backs of the rare beetles, that just because there are many more common beetles, chances are that what you have in your hand is a common beetle. And this is completely counterintuitive, right? And these kind of misunderstandings, where common sense goes against what's actually true, are at the base of many, 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 many problems. Okay, Thiago, what's the point? The point is that you have to take into account the priors. Another good way of saying this is that extraordinary claims need extraordinary proof. Extraordinary in respect to what? In respect to your prior beliefs. One thing is, I claim that I am from another country. I say, oh, by the way, I'm Spanish. There are many people who live in Spain. It's not uncommon. It's rare in comparison. It's rare to find a Spanish person in Brazil, but it's not amazingly rare, right? I mean, other thing, completely different. Something completely different is me saying that I'm a Martian. You would not believe if I told you that I'm a Martian. You would want extraordinary proof of it. So the bottom line is that you have to think about your priors. You have to think about the prior probability. You have to think about your, and let's use a loaded word here, prejudice. And the things that if you need a prior, you have to take care on how you choose this prior, because it goes into the calculation. Well, let's go back here a second. Directly into the calculation of the probability of your data, of your parameters, of your constants of nature being what they are. But if you don't use priors, and say, oh, I'm doing non-Bayesian statistics, I'm doing frequencies, I only care about the limit. But Bayes' theorem has to be, is a mathematical theorem, so it has to be satisfied. So you're just not, you're just assuming some form for your prior that you may not even be aware of. And then statisticians come to us and say, oh, this is completely wrong. One more example, okay? And this is funny, or at least it's supposed to be funny. I know millennial humor, but still. Did the sun just explode? Let's assume it's night. So you have a neutrino detector. If the sun explodes and goes nova, the neutrino detector should detect the neutrinos. Of course, there will be more problems, but let's assume that we want to know that if the sun exploded before the rest of the problems find us. Then the thing is that it detects the neutrinos, and then it rolls two dice, two six-sided dice. If they both come up 6, it lies to us. Otherwise, it tells the truth. And then you activate it. Detector has the sun go nova. And then it will roll the die. It will roll the dice and say yes. What do you do with this information? If you are a pure frequency statistician, you would say that the chance of the detector lying is 1/36, 2/6. So 1/6 for the first die, 1/6 for the second die, which is it's very small, right? It's less than 5%. So you could come to the conclusion and say, oh, I assert with 95% confidence level, right? There's only a 5% chance that I'm wrong. By the way, it's not really that, but when I say 95 confidence level, I mean, if I were to make this exact prediction, the 95, many times, I would be writing 95% of them. And then that's what confidence level means. And I would say, since the probability is less than 0.05, I conclude with 95% confidence that the sun has exploded. And then the Bayesian statistician knows that the sun does not have a random chance of exploding at every given moment. So he's much more confident that it has not exploded. And then he obviously bets money that it has not. By the way, this is obviously a useless bet because, sorry, it's a completely safe bet, because if he loses the bet, there's nothing that the other guy can do with the money because the sun has exploded. Okay, Thiago, this is all very nice and cute. What do we actually do in the end? So first thing, you want to estimate something. What's the true mass of the electron? You want to find your best estimator of the electron. So you want to find a single value that is as close as possible to the true thing that you want to measure. So do some measurement, do some estimation that gives you the mass of the electron or the mass of the Higgs boson. And what we usually do is we do the so-called maximum likelihood estimator. So we take the likelihood and we maximize it with respect to the parameters. And you can prove mathematically that this is optimal in some asymptotic limits. But then you want to have an uncertainty, right? You want to say, oh, I want to say that there is a 68%, so 1 sigma probability that the mass of the electron lies in between this and that. And then this is easy in one dimension because there is a prescription called Neyman construction with Feldman-Cousins unified approach, but it's essentially one algorithm that tells you how to do it. In n dimensions, everything is complicated because in n dimensions, you have multiple parameters, and then you can ask yourself, okay, but many different shapes, let's say θ1, θ2, many different shapes could contain 68% of the probability that the right number, that the right values are inside it, right? You can have something obvious. Oh, it's 68% that is here. Or you can have something completely crazy. Something like this. So the answer to this is that you use something called profile likelihood, where you maximize the full likelihood at each value of the parameter of interest. What does this mean? This means that you take your likelihood and you maximize, you take only the parameters that you care about. And for each of these set of parameters that you care about, you maximize it with respect of all the rest, until in the end you get something which is only dependent on the parameters you care about. And this is the so-called profile likelihood method. Thiago, I don't understand, what are parameters that I care about? For instance, one of the parameters that I care about could be the cross-section for a new physics process. And observed cross-section depends on a lot of things. On the true cross-section, of course, which is what I'm interested. But on the luminosity, on the calibration of the detector, on blah, everything. Of all these systematic effects. I don't care about these things. So what I do is that I profile my likelihood such that it becomes n-dimensional, where n is just what I want. So here I care only about the true cross-section. And I do this by separately finding the maximum, so maximizing the likelihood for every other parameter. And then it becomes something simple. It becomes a one-dimensional thing again. There is one more step that you may do, which is called hypothesis testing. This is yet another part of statistics, but it is related to what we were discussing before. Besides measuring, you may want to choose in between two different hypotheses. Again, taking a leaf from the COVID book, null hypothesis. The vaccine doesn't work. Alternative hypothesis. The vaccine works. You want to test which of these two things is true. And you do that by running the tests, the trials. And then you have to do statistics. But in the end, the question you want to answer is this or that true? Notice that this is different than asking yourself, what is the efficacy of the vaccine? But the methods, the questions are related. And therefore, the methods are related. So here, let's go back to physics. Consider two hypotheses. H0 is what we call the null hypothesis, for instance. So the standard model is a true description of nature, or the scales proved by the LHC. H1 is the alternative. For instance, whatever, not the standard model, is a true description of nature at the scales probed by the LHC. And then you have the and then the parameters are different. And then the likelihoods are different from H0 and H1. And then you have to test the two hypotheses are given each other. What do? You run this so-called statistical test, where you take all of your observations, you order them from least extreme to most extreme. What does this mean? This means, let's say, from most probable to most improbable. And then you choose a cutoff alpha, which is a smallish number. So for instance, the 5%. And then the key thing is that you reject the null if the thing that you actually observe is in the most extreme fraction of observations. And then by construction, alpha is the probability of rejecting the null when it's true, and beta is the probability of not rejecting the null when it is false. Thiago, this is complicated. Here's the example. It doesn't matter what is in the histogram, right? It's actually the profile likelihood, it's a ratio of profile likelihood, sorry. But it can be anything. The point is that assume that the standard model is true. So if the standard model is true, the thing that we would observe would follow, just by random chance, would follow the yellow distribution. While in the alternative case, oh, the Higgs boson is actually a negative parity particle instead of being a positive parity particle. You would have the blue. You can see here that there is some overlap, which means that yes, it's not perfect. It's not a 100% separable thing, but fine. This, by the way, are called a scalar and pseudo-scalar hypothesis. And then you run simulations to find out these two distributions, and then you check where, with the true data, the actual number lies. And it's this thing here. And then you ask yourself, am I so far away in the tail that it's much more probable that the true distribution is the yellow and not the blue? And so far away is the alpha, is the smallish number that I just said before, the 5%. You choose this number. Of course, you have to choose something reasonable. It has to be smallish, or else it makes no difference. And if you do this observation, and it is the case here, the weight of the blue distribution to the right of this point is less than 5% of the total. This means that I can conclude with 95% confidence level that the Higgs boson has positive parity, is 0+, is a scalar, and not 0-, a pseudoscalar. But there is something else. this is not enough to actually take a decision. If you want to say, oh, I actually discovered that, I actually conclude that the Higgs boson is a 0+ particle. Or in general, a discovery of a particle. Oh, I conclude that there exists a particle at 100 with mass of 125 GeV instead of not existing, so falsifying the null. And this requires 2 more inputs. And by the way, you should take into account these inputs when you choose the choice of alpha, which are first the prior belief, so standard model versus new physics, not existing Higgs versus existing Higgs. You choose the hypothesis, you choose the prior beliefs, and therefore you choose which alpha you want to put. And the cost of the type 1 error, so rejecting the null when it's true, versus the cost of type 2 error, not rejecting the null when it's false. So the cost of making a false discovery versus the cost of missing a discovery. What do we do in the LHC? We have what's called a thumb rule. We have a criterion. To put a limit on something beyond the standard model, we ask for 95% confidence level, which is more or less 2 sigma, right? If we want to find evidence of something, we want to say that something new exists, or something not even new beyond the standard model, but something that was not observed until now, we say that with 3 sigma evidence, so 3 sigma is what? 99.80 something %, right? We say that we write a paper saying that there is evidence for this particle. And with 5 sigma, which is 99.999, I don't know how many, but it's something like 1 in 2 or 4 millions. 5 sigma, we write the paper saying discovery of such and such. But these are numbers that we chose by ourselves. It's not a really one size fits all. Different fields may have different criteria. Still, tradition is what it is, and in the LHC, I'm pretty sure that we're going to use the 5 sigma criterion until the end. Okay, let's go through a full example, okay? And this is the end, this is going to be the end of the lecture. Let's imagine that I have the following situation: electrons and positrons colliding, and you can either have leptons in the final state, which are clean, right? You have 2 muons or 2 electrons, or hadrons in the final state. You have 2 quarks, and then these quarks hadronize and give hadronic jets, and there is a lot of particles in the end. So if you are in the energetic region where only 5 quark flavors contribute, so not the top, and below the Z boson resonance, so center of mass energy under 90 GeV, if you run the calculation, you get that this ratio of sigma hadronic to sigma leptonic, so number of events with hadrons produced over number of leptons, events with leptons produced, is the number of colors that exist in QCD times 11/9. The number of colors that exist in QCD, we now know it's 3, but let's assume we don't know. So how many number of colors, how many colors we have? Thiago, but it's easy, right? Because you have to count the number of events with hadronic and leptonic final states. But assuming that the cross sections are this, assuming that the luminosity is the same in both cases, which usually should be the case, this comes to these events with hadrons now over events with leptons. But how do you know if an event has hadrons or leptons? Perhaps these are all leptons. Perhaps these are hadrons. Do you actually really know? So one thing that helps us to separate is that events with a large number of charged particles come from hadronic processes. And with a small number of tracks come from leptonic events. But this may not always be the case. Sometimes, as I said, there is noise. There is particles that come from somewhere else. There may even be true physics. For instance, here this neon can radiate a photon that can give, I don't know, yet two other particles here, and then you have two more tracks. You can't really know. But you have some handles. One of these handles is the number of charged particles. So because there is some overlap, each selection has an efficiency to select a given type of event. And this is the cut that I told you before. So this, you make two hypotheses. Hypothesis one, hadrons. Hypothesis two, muons. And this is the number of tracks. And then you say events which have less tracks than these are leptonic events, let's say muons. Events with more tracks are hadrons. Sure, it's very good, but there is this small part here that you got it wrong. There is still background to be subtracted. And then the number of events that you actually, and same thing here, some leptonic events, you miss them in your cut. So the number of true events of a given nature, hadronic of leptonic, has to be corrected by the efficiency of your cut, and this is what you actually measure. And in practice, what we have to do is estimate these efficiencies. In general, the efficiency is not only due to the cut, but also has, as I said, the efficiency of actually reconstructing the leptons and the hadrons, the efficiency of triggering the event. Remember, you have to do some kind of online analysis to see if you throw away the event forever or keep it for further analysis. I spoke about this at the end of last lecture. The geometric acceptance. So you have to take into account all of this, and then you estimate your subtraction, your background, do the subtraction, and correct by the efficiency. You have to take into account the statistical uncertainties. Every time that you're counting, for instance, you have a Poisson distribution, and you have to take into account the uncertainty, the Poisson uncertainty. So you count, this is the usual square root of n that you learn in statistics. If you are counting, if you're using counts, event counts to measure an efficiency, oh, how many events pass, how many events fail, maybe you would prefer to follow a binomial probability distribution. And then there is all of the other things that are not statistical. There is no standard procedure. For instance, so maybe your detector is better, works better to detect leptons than to detect hadrons or vice versa. So you have to correctly account of that. Just an example. Or maybe tracks from leptons are easier to reconstruct than tracks from hadrons, so on and so forth. So you have to do your study about that. If you actually do this, turns out that if you disregard some resonant states from QCD, and you are in this region with square root of S above 10 GeV, so disregard all of this region, and you are under the Z peak, so you also disregard this region, this data is given, the result is given by this number, which is more or less 11/3, if you do the fit, which gives you that the number of columns is 3. So this is an example of doing an analysis to measure a parameter in your theory. Okay, to finish, tools of the trade. How do you actually do all of this? The standard in energy physics is something called ROOT, which is a modular scientific software toolkit. Essentially, it does everything. You want to do histograms, it gives you, you can do that. You want to do fits, you can do that. You want to do cuts, it does that. You want to sum for Lorentz for vectors, it's there. Root, you want to save your data into disk in a specific format that's used by that's good for the experiments, it does that. Root has literally everything that we need. And it's used by, but of course, because it's developed by the people at CERN. So it's used by all the LHC experiments. In other fields, of course, there are different tools. SciPy in particular is agnostic ecosystem of package that's not particular to energy physics, and it's used everywhere: mathematics, science, engineering. Particularly the numerical part of SciPy, NumPy, and some other packages like pandas and stuff like that, like TensorFlow, PyTorch, Keras, is used in the field of machine learning. And there are already some efforts to build some bridges in between the two things, because sure, Root is very good for us, but the people working with SciPy and NumPy are doing great progress in machine learning, which, as I said, is something that we are always using more in the LHC. So this is all that I have for today. I invite you to look at this package, and there are tutorials in the web, so on and so forth. And I think this is my last slide for today. Thank you very much. So let's go to questions first. Yes, I will. I'm sorry I didn't put yesterday's lecture in the Google Drive. That should make it appear in the YouTube playlist. Sorry for that, but I will put it now together with this one. And I'm just scrolling through the chat to see if there are questions. Yes, I will publish yesterday and today's class on YouTube. A question from Danielle. The difficulty in understanding a machine learning algorithm behavior, could it be solved using explainable artificial intelligence algorithms? I don't know what are explainable artificial intelligence algorithms. I have heard the name, and yes, that's what they purport to do. Do I understand explainable AI? No. Do I know do I know people in high energy physics trying to apply explainable AI to our problems? Yes. If you know explainable AI and you want to work with us, do I have a job for you? Yes. Okay, good. This was easy. Yeah, people knowing that People are using Keras and TensorFlow and PyTorch. Yes, they're very good tools. I have a student that's also using them. And yes, there is a gap to fill. There are a lot of gaps to fill. The field is literally on fire right now. Everybody wants to do this. Okay, so please raise your hand if you want to say something. Go ahead. If you want to ask anything at all. Okay, so I think there are no more questions. So I will first stop the